Welcome to another CO2 Unfiltered. We continue to learn and grow with CO2 together. This is what it's all about. Share knowledge, helping us out, different people out in the field. And I see a bunch of you consistently coming back each week to learn a little bit more, to grow a little bit more. One of the big things is you got to share this knowledge. This is what Refrigeration Mentor is all about. We do tons of CO2 training programs. We train thousands of technicians all around the world. The big thing is that I always want the students to do, the people watching, is share that knowledge. This is how we all get better. So the more people that share the knowledge, the better we all get. The refrigeration industry is only small. We're a small industry, a couple million people in this industry. One of the industries that takes care of so many billion people around the world with food preservation, medication, and we see CO2 continuing to grow. And this is why I find all the experts from all around the world so we can chat about it, we can learn from them, and we can grow from them. That's what it's all about, is how do we all get better together? And I got my good friend Jonas here today. He is the vice president of technology for Vitalis. I met him first time maybe 3 years ago or 4 years ago in Germany at Teco. I can't remember. Maybe it was 3 years ago at their manufacturing facility in Germany. What an amazing spot that was. I really enjoyed that time there. Lots of good conversations. I got to see their processes there. And Jonas has been doing this for a long time, designing, implementing, service, maintenance, and you name it. He's been involved with it from start to finish. And today we're going to be diving into CO2 oil management. This is one of the things that even for me, when I was a technician 20 years ago in the field, oil was a difficult topic. I didn't really understand it, how it flowed, the problems you could have, and this is still a problem today, even though with all the knowledge that we have out there. And then with CO2, it just adds another layer of dynamics, which we're going to get into today. So stick around to learn about the service, the maintenance side, what we're going to get in. Jonas, welcome to CO2 Unfiltered. How you doing, my friend?
Good morning, Trevor. Thanks for inviting me. Thanks for having me here. And
Yeah.
also hi to the audience, wherever you're joining from. Good morning, good afternoon. So here it's good morning in BC in Canada. And yeah, I'm really happy to be with you. And
Yeah. This has been
as
a
as
long time coming.
yeah, as you have said, like I'm in the industry quite a while already. So initially started like almost 18 years ago with an apprenticeship, worked in the field, in the service, a little more process industry. Nowadays, just CO2 refrigeration, which is a lot of fun, I would say. And yeah,
Yeah, no, I'm excited about this. We've been talking about this for almost like 2 years, trying to have a conversation because we see each other at events, and we chat about this is what we do. We chat about CO2. We learn from each other. We're trying to how do we help our customers out a bit more. Like lately, Jonas has been going out to a lot of field startups. So he works at Vitalis out in BC. They've been selling lots of CO2 equipment now, and he's been out there with the contractors in the field, just helping train them and teach them. And one of the things that we've always talked about is like oil management, CO2 oil management. This is what technicians need to know because this is going to help them grow with the dynamics of CO2. And I think we should just dive into it.
yeah, sure. So um, CO2 booster systems, they do have some, let's say, bigger challenges for the oil system, oil recovery, and all that stuff. So that's what I want to dive in today. I would like to start with some fundamentals. As most of you guys are probably aware of, CO2 CO2 systems, they're very often in a booster configuration. So you have low temp and medium temp compressors. And as this is one general circuit, they both run on the same oil. So that's quite unique because both compressors actually operate in a different operation condition, but they need to use the same oil, which is a pretty wide range for the operation. And why do we actually have oil in that system? In CO2 systems, we typically have the reciprocating compressors, as you can see here, a little simplified cut model. And these compressors, they basically just need oil for lubrication. That's very important. Every compressor works a little different. So here you can see these oil circulation discs. Other compressor, they also come with oil pumps, so forced lubrication. So there are slightly differences, but at the end of the day, they all do the same thing. They have the main task to compress the CO2, but they need lubrication, and therefore they will also displace some amount of oil.
Jonas, what is one of the biggest things that you notice? Because you work with a lot of technicians and contractors and industry professionals from around the world. What do you think is the biggest misconception, or what's one of the hardest things for people to grasp with oil?
Um, that's a very good question. Um, I mean, many people maybe think it's very easy to just fill the oil into the compressor and the compressor is displacing it into the system and it will just travel around, come back to the compressor, and then it's back at its place. It's not that easy. So there's definitely that worked for some F-gas systems and stuff. With CO2, it's a little more challenging, but we'll dive into that pretty much the whole session.
Well, I think one of the things too is we'll talk about it later is that miscibility, right? With
Yeah.
CO2 and oil. And we're going to dive into that deep. But that's one of the things that a lot of people, I think, we don't think about a lot. And I see on your screen right there, you got two different type of oils that potentially can be used, POE
Yes.
85 and PEG 68. And I think that right there is a whole session in itself talking about the difference.
100%.
But do you want to dive into that a little bit?
Yeah. So the main difference, as I said, like I just a little different to HFCs or other refrigerants, is definitely the high density because of the high pressure of the CO2. And you always need to keep in mind this CO2 vapor that's so high dense, so thick, it affects the oil way different compared to other systems. So that's the main reason why though so many things are differently. And as you have mentioned, there are typically two common oil types with CO2. The one is the POE, typically 85 centistokes, and the PAG, 68 centistokes. So we can have a look on the main differences between those two oil types. The POE oil is very commonly used in normal refrigeration, either commercial but also industrial. It's a little less hygroscopic. That means the oil itself doesn't like saturate that much with humidity out of the air, but still you don't want to have the oil just sitting there open to the environment, right? And the miscibility with liquid CO2 is definitely a good point because the POE oil is mostly solving completely within the liquid CO2. That's totally different to the PAG oil, actually. So the PAG oil doesn't like CO2 that much, so it doesn't solve that much CO2 vapor, which makes it more stable all over the different operation conditions. Like the viscosity is very stable. That also leads to less foaming, which is pretty nice in the compressor because the foaming will always multiply the oil carryover of the compressor itself. But the other part of that is it's way more challenging to handle that oil in like a normal oil return because it's separating from liquid. So you will have sometimes trapped PAG oil inside the liquid lines. And also if you have flooded systems, because that's what these PAG oil is many times used for, CO2 flooded systems, heat pumps because of the good viscosity properties or chillers. In these systems, you have this density inversion point with the liquid CO2. That's quite interesting because the oil is typically sinking to the bottom of the liquid phase, like in ammonia systems. But as soon as you go lower in the saturation temperature of the liquid CO2, it basically starts to swim. So there's more or less like a application limit. If you go too low, that can't separate the oil anymore. That's
So
why
that means So that means like the liquid, depending on the saturated temperature, the liquid CO2 would be on the top and the oil will be on the bottom. But when we start to drop in that temperature, you're saying that oil will start to float in the CO2. Is that correct?
yes. And
Okay. Yep.
typically we would try to separate the oil with like oil drops and stuff. But if
Yep.
you go too low in the temperature of the liquid CO2, it will just start to flow up, and then the whole system and the oil recovery doesn't work anymore, right?
Yeah, because that oil needs to go back to those compressors. And now if the oil's in the CO2, which is not supposed to go back to the compressors, that's a major issue. I want to just talk just a little bit about the viscosity too. So you like
Mhm.
80, POE 85 viscosity is not as stable as PEG 68. So when we talk about that, so when we say POE 85, as the temperature starts to rise, for an example, in the discharge, our viscosity starts to change a lot more than 68. Is that correct?
Yeah, the main fact for that is not actually the temperature. The temperature definitely impacts the viscosity, but it's the solved CO2 vapor, because the amount of solved CO2 vapor compared to the pressure changes the viscosity a lot. CO2 is not a good lubricant, so the more CO2 you solve, the less good the oil is lubricating. So that's the main factor here.
Okay. So that means that because with the PEG 68, it separates, like the oil's on the bottom at the right saturated temperature and the CO2 is on the top. But with POE 85, for an example, that can be just mixed together and that's coming
Yes.
back to your compressor, which is a no-no. Okay, great.
Yeah, I mean, you want to have that steadily coming back, and that's working with POE pretty good. On the other hand, it's more difficult to operate flooded systems with POE oil, because you need to be sure to separate the oil out of the liquid
Yep,
oil.
makes sense.
For that, you typically have this little tiny internal heat exchangers to evaporate all the time, little bleeding oil mass flow. I've also prepared this little liquid CO2 phase separation diagrams for both different oils. So don't want to dive into that too much, but you can see very easy the POE oil here. It has a very huge, completely solved and miscibility area. Compared to the PAG, the main area is complete phase separation. So that's a
Big
huge
difference.
And I added that note here, so it's very important to consider that for pipe routing in the field.
Because we know like all our systems that we pipe out there, we always want to slope backwards to the compressor. So, you know, all of our oils always coming back. We don't ever want to go just out to the slope to the evaporators because those evaporators will fill.
Yeah,
This is piping 101. So that doesn't change for CO2 systems.
that doesn't change at all, but the consideration that the liquid is not mixing with the oil is just bringing totally different challenges for the liquid lines, basically, right?
Yeah.
And but the PAG oil, that's most of the people probably never work with PAG oil. So I just want to talk a bit about that to make people aware there's something else existing. But I want to dive in more into the POE oil because that's the typical refrigeration oil, let's say 90% of the time used. And to get a better understanding how this relation between pressure and temperature and the resulting CO2 solution basically with the oil works, I pulled up this little Daniel plot diagram. So you can see here the temperature of the oil itself and the pressure here, these red lines. And considering that for the lubrication properties of a compressor, this pressure lines here equal the crankcase pressure inside the compressor, right? So the different pressures, so the higher the pressure goes, the lower the viscosity here gets. And also you can see these lines, how much CO2 is actually solved in the oil. So this one is 100% oil, no percent or 0% CO2. And then with the higher pressures here, it all goes up to a higher CO2 saturation. To get that in a little relation, what's good, what's bad, I put some colors over it. So typically you want to stay above 10 centistokes, which is a very good lubrication level for the oil inside the compressor. And below 7, you can't definitely lubricate the compressor anymore. So you have like a green, yellow area, and you want to stay outside of the red area. And if you draw the line here for like a saturation temperature of -5 degrees Celsius, you see the area within the green is very small. So it's basically a tiny area of the POE oil where you really rinse the compressor to survive.
Yeah, yeah. Yeah, that is a small area. So, and this is why you're saying as that pressure goes up, that what are the things that starts to drop the viscosity then? So temperature would be one. What else is, and it's pressure the other one? So as the pressure
Yeah,
goes up, the
yeah,
temperature
like
goes up.
the pressure, it's same like a bottle of sparkling water, right? It's closed, you have a high pressure, so the CO2 is solved inside the water. As soon as you open the bottle, you drop basically the pressure and it starts to gas out of the water. Here it's the oil. It's the same effect. So the higher the suction pressure gets, the more oil gets saturated by, the more CO2 gets saturated from the oil. So the viscosity drops. The temperature is one part. Let's say that way, you can change the suction saturation temperature, right? You need it to maintain your cooling capacity. So you're more or less stuck with that. But you can take care of having the right oil temperature inside the compressor to be in that green spot or maybe in the orange spot, right?
Okay. So yeah, it's all coming back to actually the oil temperature itself.
Yeah.
Yep.
And the oil pressure or the CO2 pressure with the oil is important for oil storage and oil separation, but just in the compressor, it's not, you can't change it basically, right?
That makes sense.
Let's have a look on the system design itself. So these are pretty simplified system PIDs, I would say, and they're basically two different oil secrets. The one is the primary oil secret, which is where the oil belongs to. So basically the compressor, oil separator, and the oil reservoir. And then there's the secondary oil secret, which is as soon as the oil travels out into the system, to the gas cooler, into the supermarket, in the cold storage rooms, evaporators, and that's basically
It's not ideal because we want to keep everything at the rack. We want, like, this is once again no different than like an HFC system, or synthetic. We want to keep the oil there in these multiple or parallel rack applications. This is a booster configuration. But when the more oil that travels out in the system, that means the more oil we would have to add to it, and we can't just add and remove oil, because I see
yes.
this is what's happening out there. People will go out and they'll add 5 gallons and be like, oh, we got oil coming back now. And it works for a few days. And then all of a sudden there's no more oil again.
Yeah, 100%.
Okay.
And also in the primary oil secret, you can handle the oil, right? You just refill as needed to the compressor. You have it stored in the oil reservoir. As soon as it travels out of the system, or you can't really control it anymore, right? You need to rely on the oil return in the suction lines. It's just a good guess to hope to not get any liquid or oil slugs coming back to the compressor. So that's not very easy to handle. And there are basically two different factors which are important for the differentiation between primary and secondary oil secret. The one is the oil displacement, because the higher the oil displacement of the compressor, the more you also get out into the secondary secret. And the second most important factor is the efficiency of the oil separator, because whatever amount you can separate from that discharge line, that's the good oil, I would say.
Yeah. Because there's nothing that's like 100% efficient, because nothing will go through, right? But it's important that we need to make sure like the pressure drops across is correct. We need to make sure it's not plugged. We need to make sure the temperature of the viscosity of that oil doesn't get too hot, or even too cold potentially, you know what I mean? And so these are all the things that we need to look at as technicians, when we're out there servicing. Don't be just going adding oil and removing oil. There's situations we'll talk about where you might have to do that to figure what the problem is out. But if you put in 3 or 4 gallons, you need to take 3 or 4 gallons out, especially if it's been running for years. Like startup, this is where everything should be taken care of.
Yeah. And whenever, like as long as you don't have a leak, but you miss after a while some amount of oil, there's a reason for that, right? if you're just, without considering any measurements, refilling the oil, at some point it will come back and potentially destroy compressors or reduce the efficiency in the evaporators, right? If you just trap all the oil in the evaporators, obviously the oil is not a good heat transfer fluid, and it's not evaporating. It's not making it cold. So you want to have the CO2 inside, not the oil. And that all affects to the system's efficiency and especially the reliability of the system. And this is a very simplified diagram. And especially for technicians, that's not what they see typically. So
what are the, I should ask you this, what are the 3 or 4 different designs that you have seen? There's low pressure, there's high pressure. I see some with separators, some without, so reservoirs and some single reservoirs. What are the most common ones that you see and the ones that you guys design with? So there's a few different ones.
So for these typical booster systems, you do have, we go back to this picture. That's very normal to have an oil separator, then draining the oil back into the oil reservoir, which is stored under lower pressure, and then you feed that back to the compressor. That's the most common way of oil systems. Let's talk about that in the next slide, because that's when I with the more detailed P90, let's say. Just want to show a picture of a wheel unit. That's how typically the technicians see the site. So don't want to bother too much with just theoretical P90s. But we are jumping right back into a P90. So this is a very generic P90 of one of our systems. So we do have the medium compressor staging here, the discharge line, a heat reclaim, the gas cooler, high pressure valves expanding the CO2 from the high pressure side down into the liquid receiver. Then the liquid line is providing low temp evaporators and the medium temp evaporators. It's one common liquid line. And the LT evap's are connected to the low temp compressor suction, which is discharging back into the medium temp suction line, where also the flash gas is bypassed from the receiver into the suction line. Then an internal heat exchanger to maintain the right suction temperature, and that goes right back into the medium temp compressors, right? So that's the typical design of a CO2 booster system.
And this is the most important thing. I do a lot of CO2 trainings. I train a lot of people around. This is the number one thing that you, as a technician, you need to learn. You know what I mean? Like Jonas, when he's going out there and meeting with these technicians, this is what he's pulling up and showing the guys. This is where you got to find all the components, because sometimes there's a lot of components on these systems. You know, you got 4 compressors on the top end, 3 on the bottom end, and there's a lot of components, and these are built up systems. So you really want to make sure that you know all the components on there, especially when we get into the oil circuit, because those components are very critical to the system functionality and the system efficiency.
Sometimes it's just easier to understand if you want to isolate whatever section for service or maintenance. It's sometimes much easier to just chase that down into the P90 and identify the isolation valves or what strainer to change. That makes it sometimes easier to work off the P90. Sometimes it's just easier to find the root causes of issues just on site by chasing the lines back to valves. And I mean, obviously, listening to components is sometimes very helpful. Touching, that's the real technician world. It's touching, feeling temperatures, and listening to components.
I love what you just said there, though. That this is something that's not lost yet, but the difference between an experienced technician and someone that is less experienced. Because I know friends that can walk into a rack room and they listen and they're like, I know that compressor right there, probably number 3 is the one that's running into it. There's something going on. It's not right. Or they listen to a valve and the way the valve is moving or opening and closing, they're like, that there's something wrong in there, that like the gear, there's a skip in the gear. And this comes with experience. I love that. It's touching, it's looking, it's seeing, it's smelling.
Yeah, even smelling sometimes, yeah. And like listening, you can clearly hear if the system shuts down, but you still hear like a little blowing noise coming out of a high pressure valve or flash gas valve, injection valve. You know, okay, there is potentially something stuck, some dirt, some debris stuck into the valve seat. So it's still way more about feelings than just going through all the documents.
Yep. Yeah, I
That's
love that.
my opinion. But coming back to that topic, I mean, we want to focus on the oil system here. So I zoomed a bit in here to talk about the oil system we have here in the system. So you can see here the medium temp compressors pushing the whole mass flow through the separator, where most of the oil should be separated. And there's a little level switch at the bottom. And as soon as the oil separator or the oil inside the oil separator is reaching that level, it basically activates this little return valve, which is typically a solenoid valve. And this drains in a pretty steady interval. Whenever the level is reached, the oil back into the oil reservoir. We do have a little tiny self-made block here, which includes also a strainer upstream and a little side glass downstream, because we just talked about it's nice to just look inside what's really coming back and see the oil quality coming back. As soon as we drop the high pressure down, or the high pressured oil down into the oil reservoir where it's stored to get supplied to the compressors, with dropping the pressure, we have basically the same effect we talked earlier about. So the lower pressure is degassing the CO₂ out of the oil. So we reduce already the CO₂ amount inside the oil to have as pure as possible oil. And the, let's say, separated CO₂ vapor is then bypassed in this little tiny line that goes, we've seen that before, all around to the liquid receiver, which sits on a slightly higher pressure than the medium suction. So we still have a very good maintained differential pressure to supply the oil back into the oil level regulators. And then also a main strainer is typically a very good idea to have, because there are sometimes either dirt generally in the system, or you have some failing components, which can lead to contamination of the oil cycle. And that typically affects the compressors very directly. So that's why we put in two strainers actually here to just filter out whatever is caught inside the oil separator. And in case we still have some remaining debris somehow coming into the oil here, we still have a strainer again to make sure that a very clean oil is supplied to the compressors.
Yeah, I think this is important because you got to understand all the components for maintenance, because this is one of the things that I've seen, Jonas, and all the trainings, like especially with new technicians who've not done like an oil maintenance before. They've done it on HFC, but they haven't done it on CO₂ yet. It is not really any different. The pressures are higher, but the oil system may have a few more filters in it. So strainers and filters, these are some of the things that do need to be checked, as well as probably replaced at some point. So in like Jonas's manual, they will tell you the intervals that they want you to look at and do these tests. So it's in checks, because that is so important. I think I've seen over the last 2 years, maybe a dozen or two people that I work with where they're like, Trevor, I didn't do the oil maintenance yet because nobody's taught me, or they never showed me and never had the opportunity to learn. But after they did it, they're like, it's the same as HFC. You know what I mean? In the processes. Is that similar?
At the end of the day, yes. I mean, you just need to isolate the valve around the strainers, especially this one. This is the most important strainer here because it's the first in the oil line. And it's basically the same thing. You isolate, you try to drain as much as pressure out of that little section into the reservoir, isolate downstream, and then make sure to depressurize the section. And then it's basically just opening a strainer body and cleaning the mesh and changing it if necessary, right? So that's pretty normal mechanical work. But let's focus a bit more on the oil separator. So I've put in here a picture of like a very, I mean,
What's it?
I don't know how I should call that. But there are some generally different aspects which applies to CO₂ separators compared to normal separators. So as I've mentioned before, the CO₂ vapor here, it's very thick gas. So it basically, especially in the high pressure discharge line, you sometimes run up to 100 bar. And this gas gets so heavy that the oil drops are not really dropping down. So what we know out of F-gas or ammonia, that we have centrifugal oil separators and stuff like that, that's not really applicable to CO₂ at these pressures. So that's why these coalescence cartridges got in place with the transcritical CO₂ systems. And the thing here is the coalescence cartridges, it's a very fine mesh. It's pretty much the finest mesh inside the system. So it catches all the fine debris which is traveling through the whole system. And with the high pressure and the high differential pressure actually affecting the oil cartridge while clogging up, creates a very high force on that cartridge. So that's why you sometimes see those cartridges exploding, basically.
And that's one check that you need to do as a technician. You need to, what's your inlet pressure and what's your outlet pressure and what's that differential? This one here would be zero because there is nothing
Yes.
there. So if you get zero, it's bad. So you can
Yeah.
usually, what's great about CO₂ systems too, there's pressure transducers everywhere. But if you're going to do it with gauges on this, you need to use high pressure hoses because, like Jonas said, it could be 100 bar, 1450 psi. So make sure you that. Now, if it's 25 psid differential, that's another issue. You know what I mean?
Yeah.
That means we're
100%.
up. So I think it's it's a low differential, 2-3 psi, 0.3 bar, maybe, you know what I mean, that you should have kind of regularly, right? Is that around the right range, Jonas?
Yeah, I mean, in general, there's a recommended DP existing for those cartridges. For ours, it's 0.5 bar.
Okay.
So that's more or less like you want to stay below that differential pressure to not run into any issues that the cartridge is basically breaking or blowing up. But I mean, on those cartridges, there are some different aspects to consider while designing that. And back in the days, while I've still been at TECO, we have seen a lot of issues with that in the field, and started basically to test and design cartridges. And we figured out that there are some special needs on the general design. So I just want to show like this cartridge style and this cartridge style. So one very obvious thing you probably notice here is that this reinforcement mesh at the outside of the cartridge surface is basically restricting again the flow rate of the CO₂. And by that, you actually accelerate the CO₂ flow in these little tiny holes. And what you actually want to achieve is that the oil can easily flow down and separate. But by accelerating the flow at the outside of this reinforcement mesh, basically just shoot a lot of drops back out of that cartridge, and then it travels out into the system. So that's why we designed this little special cartridge here without an outer mesh. So we made sure that we used the right components and the right meshes, which are lasting for those high differential pressures and the higher forces, but not restricting the oil separation. Little results here for a bit. So we had a test bench for oil separator cartridges. The existing ones at that time, if they have been worn, and they do typically get then some micro cracks, which is affecting the separation efficiency a lot. They've been very bad. The normal ones, if they have been new and clean, they still reached a level of like up to 90%. You can see here the compressor oil carryover. So typically the oil carryover of the compressor is around in this range, in between 1 and 3%. And with the improved design, we have seen a very high stable separation ratio. So this then leads to the effect that you basically just lose 2% of the total oil carryover into the system, and 98% stay right away into the oil reservoir. And that basically ends up that you do not need to fill in like another gallon or two into the system after the whole system is saturated, right?
Yeah, because we want to make sure that we keep as much as possible at the rack, at the system versus going out into the system. And this can happen in different ways. Like if you have bad valves on a compressor because of overheating or something, or rings, that could cause higher carryover rate. You're just pumping out oil. So there's a lot of things that we need to look at, because I think that's one of the things that we'll talk about a little bit in troubleshooting oil. But if you just have thermal imaging gun, it's such a great tool for a refrigeration technician, and go across all the heads of each compressor, and you can see right away if one's 30 degrees, hotter than the other one, there's an issue with that cylinder head. You know what I mean? So these are things to do. And then also the oil temperature of the body, like the oil temperature, just with a gun. You know what I mean? These temperature guns. So I love those ones.
And especially if a compressor had already some lubrication issues and the cylinder rings and stuff got worn out, then at some point the oil carryover is just getting super heavy.
Yeah. And then it's like, where's the oil at? Let's add some oil to it, because this one compressor has actually bad rings. It has nothing to do with anything else. So we add some oil to the unit, and then it runs for a little bit, and then it happens again 3 or 4 days later, and then until someone comes back, and it all comes back and smashes a different compressor. Now you have two broken compressors instead of just one broken compressor. So I've seen a lot of that.
Yeah, no, I've seen the same, and it's always very important. Like if one compressor fails, it's very important to do the root cause analysis, right? Figure out why did that happen. Because if you just replace the compressor, then maybe the week after the next compressor is broken and the other, then it's a never-ending story, right?
Yeah, I know in my advanced service compressor master class, like I trained compressors for years and years, and technicians are always surprised, like in the amount of details you have to look in it. It's not just all you just pull off the head and look at. There's so many like uniqueness to each different compressor, and the things you got to look for, and scoring, and rings and wrist pins, and so it does take a little bit. I know this, it does take work to do that, but like Jonas says, if you do this, you will find a root cause, and the next one's not going to fail. You know what I mean? Or shouldn't fail.
That's the ideal scenario, yeah. And I mean, the ideal scenario is that you just don't lose a compressor. That should be the main goal of
Yeah.
starting from the beginning with the right system design and making or having all these considerations in mind right from the beginning. That's reducing a lot of potential failures, but you will have failures here and there.
Yeah, because there's a lot of dynamics in this when we talk about failures. Because I talk to a lot of people, like the design could be perfect, but if the install's bad, there's going to be an issue. The design can be perfect, the install can be perfect, but the commission can be terrible. The design could be perfect, the install could be perfect, the commission could be perfect, but the service is terrible on it. You know what I mean? Or then the maintenance. I do a lot of trainings right now on CO₂, where some customers don't want to pay for maintenance. So if you don't pay for maintenance, how are you going to not prevent a compressor from failing, or something happening, losing product at the end of the day? So I always talk with the technicians is to show them the results. Like the pressure differential is an easy one. Like we got a 20 psi pressure differential. We need to change this cartridge. Like there's no doubt about it. Like you got to show them right away that has to be done pronto. There's no waiting about it. If they wait any longer and they don't want to pay, it's going to be, they're going to have tens of thousands of dollars of potential service. And it's better to be proactive than reactive. And I know a lot of technicians that come into the training program, they're just like, I want to do the maintenance, but my customers, they don't want to pay for maintenance. So it's a catch-22 sometimes. So it could be one of 4 or 5 different things that are causing failures.
Yeah. I mean, that's why it's called predictive maintenance, right? You want to, you just want to avoid to run into issues. That's why maintenance is so important. So, I mean, here, that's basically the worst cartridge I've seen in my life. So I was digging through my phone for the most impressive picture here. So I've actually seen a couple of cartridges blowing in the field, and we talked briefly about that. There is a recommended maximum DP of a cartridge, but it's difficult to use that as an indicator. As you have said, is that if the cartridge is blown, you'll not see any substantial differential pressure, and you might think the cartridge is perfect, but it's not, right? Because the cartridge is already traveling to the gas tube.
Yeah. This is where real things happen. It's not that blew, like, you know, you had a failure in your separator. It's that travels through the system and jams into your high pressure valve. You know,
Yes.
it makes its way through. That's where issues start to happen.
Yeah.
Big issues.
So that's like, I typically, whenever I'm at a startup, I always try to listen to the oil return solenoid valve, because once in a while, every few minutes, you just hear like a little click, and then you know, okay, the oil separator is doing its job, and then you do not even have to look after the oil separator, I would say. So if you come on site and want to figure out if the oil separator is doing its job or not, as long as like 1, 2, 3 compressors are running, the oil separator should return every 5 to 10 minutes a chunk of oil. And if you just listen to the oil return valve and you can't hear anything, that's the best indicator of that this cartridge needs to be replaced. Also, sometimes just closing the oil return line and wait that the sensor detects oil, but then it's not able to drain it, right? So then you have a little longer window to see that it's really separating. But that's pretty much the best indicator of the quality of oil separation and the cartridge itself. But nevertheless, just maintaining the regular maintenance intervals, especially after the initial startup, like maybe the next day, maybe the next week, that's definitely the right time to replace the first cartridge, because at the beginning, there's little fine debris out of the whole field piping and everywhere. It all gets stuck in that cartridge at some point. And to replace that right after the commissioning is very important. Then maybe a month later, and then in typical intervals, right? And then you don't run into any risk about breaking a cartridge. And that's important. We also mentioned that slightly before. Like, once the cartridge is blown and we lose all the oil into the system, it's gone for a bit. Like, it's very hard to recover that out of the system back to the compressor. Even if you change the oil separator cartridge, you typically notice, because the oil reservoir is empty and the compressor start to get an oil alarm, and then you can't return the oil anymore. So you need to refill the oil, then you need to start up the system again. And then after a while, once the oil is recovered again, you need to drain it again. So that's kind of like important to do the maintenance right and check the function of oil return valves and check the strainers before you lose all that oil.
Yeah. So on your system, do you kind of like with the solenoid and oil level design, do you do like on demand? So as it sees it change it, or is it a time cycle? There's lots of different strategies out there. Do you do like on demand? So rate as it fills up, it just transfers it over to the oil reservoir?
Yes. So it's basically just a simple level switch. Whenever it indicates an oil level, it drains it. Because if you go right off a time cycling, you potentially drain too much oil out of the separator, and then you bypass hot gas, and you don't want to inject too much hot gas into the oil reservoir. And I mean, there are different ways of doing it, but just going off the simple level switch is the easiest and most reliable way.
Yeah, I see most of them out there like that.
Yeah, like, once such a cartridge is exploded, basically, and these little tiny fibers are traveling through the system, that's obviously nothing you want to see. But if you see that sometimes causes even more damages. Like, here, that's some pictures of an oil level regulator, where basically all these fibers got stuck inside the valve seat. And then if the compressor is running, it can't refill enough oil. If the compressor is just on standby, there's a high risk to just overfilling over the time the oil level. And once it tries to start, it will just destroy itself, right? Because it doesn't want to have the cylinders full of oil. So
Yep.
that's also why we went with our design away from fibers. That's sometimes a very big cause of or big root cause of following mistakes downstream the system. But also if you ever work on a system, it's sometimes good to just look into the side glass of the oil level regulator, because even if you have some sort of debris inside the valve seat and you see that it's slightly filling, even if it shouldn't fill, that's a good indicator to just open up the solenoid once and check if there's some debris stuck inside the valve seat.
Yeah.
It's always good.
Because depending on the oil regulator, some will have screens, some don't have screens, so they
Yes.
rely on the strainer. So this is where you need to understand the components. Doesn't really matter who makes the components. You just need to understand if they have a strainer or not, because I know for sure some people, because I know these controls really well. Some people would like, well, there's a strainer in there, and then you pull it off and there's no strainer in there, or vice versa. And I think one of the big things is if you have a major like blowout like that needs to be logged. So that next technician comes back there so they understand, because you might change, just like you said earlier, you might change that cartridge, but all that crap is still in the system. And so it might
Yes.
take months and months and months, maybe even years to get some of that stuff out. And
Yeah.
that some people need to know about that, because now it's in the system and it happens. And
Yeah.
the other thing that you said is getting the oil back. I know I've worked with lots of technicians on it, and depending on the system, it's going to be harder, especially in the wintertime, even to get oil back when you have a major blowout, like hours and hours sometimes. And then when you have hot gas defrosters, different strategies than electric defrost to get oil back. So just remember it be patient with yourself when something like that happens.
Yeah. Yeah, you really don't want to have the oil traveling out into the system, because as soon as that's happening, no matter what, like it's more difficult to get that back into the oil reservoir and into the compressor.
Yep.
But that was a good point you have said. Like this oil regulator type actually came with a strainer, inbuilt strainer. I didn't edit that picture to this slide, but the amount of contamination and the amount of fibers was just that heavy. And we deal with big differential pressures in CO₂. The strainer couldn't catch obviously that big amount of fibers, and the high DP then just cracked the strainer. And then the fibers were traveling into the valve seat itself. So it's first goal is always to avoid that the contamination happening, right? And I've took some pictures out of the production to see a little more clear how the arrangement of such an oil separator is actually. So here on the right picture, you can see this little tiny oil return line goes into that solenoid strainer block. And here will be the level switch installed. And this level switch is then activating that solenoid and returning the oil into that reservoir. If you want to do the maintenance, the cartridge filter change, you can see here 2 service valves. So whenever you do that, switch off your evaporators, let the system pump down properly to shut off the compressor safely, and make sure to don't lose your goods in the warehouse, obviously. But once the compressors are shut down, you can isolate this oil separator at the outlet and the inlet. And I always prefer a little trick to drain the CO₂ as good as possible. Once you have isolated these 2 main isolation valves, you could just put a magnet on this little oil return valve and then drain all the oil and most of the CO₂ vapor into the oil reservoir. And once the pressure is equalized, you can just shut off this oil return line as well. And then you just drain half of the CO₂, right?
Yeah. No, that's a great tip. That's a great tip. And just always remember, there's still going to be pressure inside there after you isolate it. So you don't just rip out all the bolts and knock it off. You always leave 2 or 4 bolts in there, just crack so you can knock it so you get any pressure. Don't blow oil in your face. So safety, always safety first.
And like what I also like to see all the time is if you relieve the pressure out of this little service port through a gauge manifold. Even if the pressure is gone, don't close the gauge manifold. Leave it open because the remaining oil will always bubble out some more CO2 pressure. And if you close the valve and then new pressure builds up, it takes you 5 minutes to loosen the top cap, then maybe you're back at 5 or 10 bar. And you don't want to open that top cap with 5 or 10 bar. Yeah. So leave it open as long as it takes to open the top cap and make sure there's no pressure behind that.
I love that.
So that it's safe. I've also put this picture in here because here you can clearly see that's the remaining oil at the bottom of the oil separator. And you can see that it's basically just boiling like water. And that's just the CO2 gas solved inside the oil, hot oil. And with draining the pressure, it all bubbles out. And that takes minutes. So it's good to drain that oil before opening through that oil return valve into the oil reservoir. Because after you finish the cartridge change and you tighten back the top cap, you want to pull vacuum, right? And as soon as you pull vacuum and you still have 1-2 liters of oil in there, fully saturated of CO2, it will take a long time to get down with the pressure.
And I know I've done trainings where guys are like, Trevor, well, I just put CO2 in there and blow off. You don't want to do that to purge it because that moisture or something can get in there.
Yeah.
You need to pull an evacuation on this every time. It takes time to do it right because that there is going to cause havoc on your system if you get moisture in there, and acid kills compressor, kills components. So definitely evacuate it.
And another thing is, whenever you open anything in CO2 systems with an O-ring, make sure you have a spare one with you. Because the high CO2 pressure is sometimes absorbed by this rubber material. And as soon as you open it, it starts to blow up. It looks like blowing up a balloon. These O-rings expand a lot and get very thick. Sometimes they break. Sometimes it takes hours for them to shrink back in position. So typically you can reuse them. So make sure before you open it that you get the right O-rings on hand. And I've also seen a couple of times that these lock nuts on top of the cartridges get heavily over-torqued and bending down the top cap of the cartridge itself. I mean, the cartridge just has to sit tight, right? So it doesn't need a big torque. So that's something you should keep an eye on.
What a coincidence. That's in the manual and says what it's supposed to be torqued to.
Yeah, it depends on what, like I've seen different nuts being used for different oil separators. Sometimes it's this mechanical metal lock nuts. They already need such a strong torque to just spin them down. It's very hard to say like when do they really start to push on the top cap and when you're just rotating. So the easiest is to just screw it down slowly, touch the cartridge, and you will feel as soon as it's not sloppy anymore, give it a little extra spin and that's it.
Perfect.
Yeah. So this is the oil storage vessel. So the oil storage vessel, as I've said before, you want to have that under lowest possible pressure to have as much as possible CO2 gas coming out of the oil. That's why in typical CO2 systems, these vessels are connected to the liquid receiver to be slightly above the medium temp crankcase pressure, but as low as possible. Especially in smaller systems, sometimes you will see these combined oil separator, oil reservoir vessels. They might be very handy for installations, but you will always store the CO2 or the oil inside the discharge CO₂. So we have the highest possible CO₂ saturation inside the oil. And as soon as you refill that high pressured oil into the crankcase, especially low temp crankcases, it starts to expand the CO₂, and you basically just produce foam, which is not very nice for the compressors, let's say. And
So I see you got insulation on there. Is there like a heater element in that one?
exactly. So that's another thing. By lowering the pressure, you can reduce the CO₂ saturation, but also by keeping it warm, because the warmer you keep this the oil, the more CO₂ can basically gas out of the oil. You don't want to have it too hot. We have seen that at the very beginning. There's a sweet spot of oil temperature. So that's we do use a self-regulating oil heater, which is maintaining the oil at about 40 degrees C. So that's very important if you have an installation being outside, especially in enclosures. And in the wintertime, that would just cool down too much. In the regular operation, these heaters are not very often active. So
yeah, one of the biggest things I've seen, especially over the last 5, 6 years doing all this CO₂ training, is that you used to think, okay, in the summertime they talk transcritical, it's super hot, that's when most of the issues happen. For me, I've seen over the last training thousands of people, it's the wintertime where the biggest issues are that I've seen, especially with oil, like oil issues on these systems where the reservoir fills up with CO₂, and you're sending direct CO₂ back to the compressor, or you lose pressure and you don't have enough pressure because you got to be above the suction pressure to move that oil. Do you have any recommendations on when, because I'm sure you've seen this before over the time where all of a sudden your flash tank loses control, it gets too low, and now your oil pressure, you lose your oil pressure. You want to talk a little bit about that and some strategies for technicians to look out for?
yeah, I mean, that's something which mostly depends on the liquid receiver pressure. There are some ways around to maintain the liquid receiver pressure inside the controller typically. So it forces the high pressure valves to open to just drain more of the high pressure coming from the gas cooler to maintain the receiver pressure. Or on the other hand, as soon as the receiver pressure drops too low, you will also see that there's not really a liquid flow anymore through the expansion valves into the evaporators. So automatically the suction pressure on the evaporator side is dropping as well. Typically leads to the point that the compressors shut off because they reach their set point. They think everything is okay. But the real life is that the evaporators just don't get any liquid anymore. So I've seen those scenarios happening quite a few times in the field. But this is typically handled by the controller to force the high pressure valves open, or some systems have this hot gas dump into the receiver to maintain the pressure. But typically it's not really affecting the oil differential pressure, because if your receiver pressure is on the same pressure as the crankcase or suction pressure, the whole system will not work anymore. The compressor will survive without getting oil refilled in 1 or 2 minutes, but the system itself will fail if you really run into that major problem.
Yeah. Have you ever seen reservoirs fill with liquid CO₂?
Yes, I've seen that. I mean, I've built once a test system in the R&D, so it wasn't a client project. So that's totally fair to see those things.
Yeah.
We had some flooded tests with PAG oil, and I just couldn't detect the oil properly. And I was also at this limit where the PAG oil started to flow up. And I've seen liquid CO₂ getting refilled into the compressor, yeah. But as it was the same pressure as the suction pressure, just a little height difference, it didn't boil off right away. So you could have actually seen the liquid CO₂ flowing around on the oil inside the crankcase. So, but I haven't seen that in the field yet, luckily, because it's okay to do that in the lab. It's not very hard.
Yeah, exactly. I got a question. Is that an insertion heater or a wraparound band heater on the
That's a wraparound band heater.
wraparound? Okay.
And it's like we do insulate this little section to keep the heat inside because we don't use like a lot of capacity in that little heater. So it's a few, I don't know, like 60,
Watt.
80
Yeah.
watts, whatever.
Yeah.
So it's not enough to melt this vessel apart. But that's why we insulate that, right? We just want to
Yeah.
keep it, avoid that it gets way too cold. So this is the normal oil storage, I would say, which is very common in the field. We also do a little different system, which we call honeypot. The honeypot basically is an accumulator. You can see up here in this, that's a very small, tiny unit, especially made for convenience stores, where we build basically a suction accumulator in the suction line of the medium temp compressor. But we also return the oil coming here from the oil separator through that little valve. We return that into that vessel as well. So we basically store the oil inside a suction accumulator vessel on empty, which is the lowest possible pressure for the oil. And we just feed that back through that little hose to the distribution block by gravity into the medium temp compressors because there's no major pressure difference. We use the height difference to refill that oil. And by not causing a pressure loss while refilling, there's absolutely no foam inside the oil. So that's the best condition you could provide to the compressor. And we do have some good side effects as this sits on the suction side in case we would get liquid slugs back from the medium temp evaporators. It would separate that liquid in that separator as well. You don't want to have that liquid in there mixing with the oil, but it's still much better than just slugging it back to the compressor. And on the other hand, we basically route the low temp discharge through that vessel as well. So most of the low temp oil carryover gets separated in that vessel already. So that's pretty handy and an easy system because like you want to have the system as easy and safe as possible. But that has been said, or has to be said, as we just use differential pressure, it's hard to provide enough oil for huge systems, right? Like if you're thinking about industrial systems, you would need quite a huge vessel, a large height difference to really supply enough oil for these big industrial compressors. But for commercial systems, it's a very good use because the small compressors typically come with the oil disc instead of oil pumps. They're a little more critical when it comes to lubrication. So it's good to have the best possible oil quality in those compressors. But we have built those things also on some special industrial builds, as you can see here. That's quite okay sized vessel, doing the same thing as here. And then basically providing the oil back to the medium temp compressor just by height difference.
And one of the things when Jonas designs a system, his team designs a system, and whoever designs a system, there's a amount of oil that needs to be in that system. They send that to you. They tell you how much oil this system should take depending on how much pipe run there is. So they give you a good idea depending on the size of that reservoir. Because they got to go around and lubricate all the stuff because as that travels through. So you just want to understand that there is guidance. It's not like you just go and you just add a bunch of oil and then you figure out, oh, it's just the one site class. There is a strategy behind that from the manufacturer and the designer. So always go back to that legend that it'll usually says on the legend of the unit how much oil, how many liters, how many gallons it should take.
I mean, typically you want to start with like a half-filled oil reservoir, either this style of oil reservoir or the normal style oil reservoir. You will have some sort of saturation of the entire field piping and evaporators with some oil, but the better the oil separation efficiency is, the less you need to refill. So once we implemented our, let's say, optimized oil separator cartridges into the field. We have heard a lot of feedback from installers that they had to basically remove oil, which was already filled and the system was running well. Once they got a higher efficiency oil separator, they've seen after a day that they had to drain 1 or 2 gallons out of the system because it all came back, never traveled back into the system, and just got accumulated in the reservoir.
Yeah, and that's always a good sign when you can use less because oil is super expensive. What is your strategy? So on a startup, if you're going out and you're doing a startup, the systems are dry. I'm assuming there's no oil in any of the compressors or anything like that. What is your strategy after they get 150 psi or 10 bar in there of vapor? How do you recommend them to add the oil as well as test the oil components?
So I always recommend to fill the oil while you're pulling the vacuum because that's the easiest. You don't
Okay,
need to have
perfect.
these pumps and stuff and pump it against the internal pressure. And you still, in case you have some sort of water solved into the oil before it basically builds the toxic, the poison part, you're still able to vacuumize some sort of moisture out of the oil. So it's not bad to have that pulled into the system with initiating the vacuum for the whole system. And once you're done with that, you have the system pre-filled. You would start to fill your vapor to get above the triple point to not run into dry ice issues. And then you would basically just start to fill the system with liquid into the liquid line or the liquid receiver, right? And that's totally good to start up the system. And if there's some oil missing inside the compressors, as soon as you fill the system, the compressor should be filled with the oil level regulators as well. Once you start the compressors up and they're actually running and pressure builds up, you will definitely have the differential pressure available for the oil reservoir to fill oil through the oil regulators. And then in the very first, let's say, minutes and maybe the first hour, it's very good to keep an eye on the actual level inside the side glass of the compressors. If the regulators stay green, if they get yellow, that means typically they refill. And it's always good to do a loop check before you basically start that system up to just make sure if the regulators or the differential pressure switch from the compressor is triggering an alarm, it actually shuts the compressor off, right? That's a general pre-checkup of the entire safety system. That's highly recommended. But once that's done and the system starts up and operates for the first hours, it's always good to have a look on how the oil is refilling, if there's a lot of foam showing up inside glasses or not. And also if you see some sort of changed color of the oil. I mean, ideally the oil is fairly clean, maybe slightly, a very slight touch of yellow. Oil is not supposed to be dark brown, also seen many times. Also, if you do a filter change or stuff and you smell like that the oil basically smells like burnt plastic or stuff, I think everyone in the field has recognized that at some point. That's never a good sign, and that is an indicator to basically perform a complete oil change at some point, because you want to have the oil just as clean as possible.
Okay, great. So getting back to it, so you like to add the oil when it's under vacuum. So at this point, all the valves for the oil systems are open at this point. Is that correct?
If you vacuumize the entire system, you can have all the valves open as they are in the normal operation condition. You would not have the system powerized, so there is no oil regulator active, because during the vacuum process, you don't want to powerize the system. For the initial filling, if you need to refill some oil after a day or whenever, you would basically just isolate the oil reservoir, and then you could even do that if you're quick while the system is normally running. again, sometimes it's helpful to drain the pressure once that oil reservoir is isolated, to drain that pressure with the service hose into the suction line to just be quicker and don't
Yep.
lose too much CO₂. And once the pressure is drained, you either have these little pumps, they work to push in oil while the vessel is under slightly like a lower pressure.
Yeah.
But you will always pump in some air as well. It will never be just pure oil. So you would need to run the vacuum anyways. So it might go faster, but you need to run a vacuum no matter what. But you can always pull oil in while pulling the vacuum.
Yep. Okay.
And
So let's just go back to that. So you're in a vacuum, it's pulling down. You'd actually take a hose, you put it at the top of the oil reservoir on one of the service ports, and then you put it into the oil bucket, the oil can.
we typically have two connections. One is in these vessels at the top, one at the bottom. So you need to connect the vacuum pump somewhere, and that will be the top port because you don't want to pull the oil into the vacuum pump. So you would connect the vacuum pump on the top port and the oil hose at the bottom port, and then you just pull the oil out of that canister of oil. Yeah.
And then you recommend pulling it, for your example, up to about 50% of the oil reservoir or oil receiver. And then after you're done that, you're still pulling the vacuum. So now we're still pulling out all that moisture, anything in there. All
Yeah.
the other valves will be open at that time. So the oil will feed.
No, you will still have closed while you're vacuum, right? So you would isolate the whole oil reservoir. You would pull your oil in with the vacuum pump. As soon as you reach like the middle cyclers, maybe a little on top if you already assume like the system is still saturating, but you don't want to fill that completely up, right? You want to have some sort of buffer to separate the CO₂ while returning the oil, but also to have some fluctuation for oil level, basically, without draining that back through the equalization line to the
Okay, perfect. So the whole system's on evacuation, but when we isolate the oil reservoir, when we pull the oil into it, is that correct?
No, like the whole system can be in operation.
Yeah, no, but I mean on first startup. So it's a
Yeah.
empty system.
Yeah.
Okay, so your empty system right now. We're first startup. Everything's in a vacuum right now because we're just talking about first startup. You isolate the reservoir, you fill it up to half full. You take the vac pump off, then you open up the oil reservoir at this point, and then it'll feed to all the transfer blocks. Is that? I just want to make sure the steps on a startup is correct when they're doing it.
So if you pull the vacuum of the entire system, you don't need to isolate the oil reservoir.
Okay.
Right? You just pull out the whole system with a vacuum, and you just use the chance that the system is under vacuum and still continuing to pull down the vacuum to just connect the oil hose and fill the reservoir up.
Perfect. And then the other way is when the system's actually running. That's when you need to isolate it, depressurize it, and then pull it in. Just want to make sure that everyone understands the step when they're going to work on your equipment, the way to do it on a startup or when they're doing it on service. So we just want to be clear on that. So that's perfect. Thank you.
Yeah. Okay. So one more topic. As soon we talked the whole time about the basically primary oil circuit, but I want to talk a bit about what's actually happening with the oil as soon as it travels out into the system. So if you carry oil out into the system, it typically passes through the gas cooler, through the high pressure valve, down into the liquid receiver. You've mentioned a few times before something about winter cases. In the winter, it's sometimes difficult because there are very low temperatures inside the gas cooler, so you will catch some oil there as well. But typically, it's ending up in the liquid receiver and then traveling through the liquid line into the field piping. And I've seen many different ways of how the liquid line branch offs are made. So that's why I thought it's maybe worth to talk about that. So as I've mentioned before, the CO₂, the liquid CO₂, and the PUE oil is typically traveling mixed inside the liquid line. And if you have these branch offs, I always recommend to basically branch it off horizontally to the side. I've seen installations where people connected from to the bottom to basically get the pure liquid right away. But the reason why I would recommend to connect it from the side is you have saturated CO₂, so you always have a little amount of flash gas, and the flash gas is always traveling more at the top of the liquid line. So if you would pull out the liquid always from the bottom, you would always get pure liquid CO₂ to your evaporators, except of the last 1 or 2 evaporators. So that's why it's good to branch it off to the side to basically pull always the most amount liquid, but also a few of the flash gas particles to still have some liquid left for the very last evaporator in that line.
Yeah. So why wasn't this done like in HFC? What's the difference? Why in CO₂ we take it off the side versus the bottom?
Yeah, so
and you can do it. Just remember, everyone, you can do it both ways. You know what I mean? Off the bottom works, off the side. You got to go follow what the manufacturer recommends. So Jonas, he's going to send you equipment out there, and he says he wants you to take it off the side. You do it that way. Other manufacturers may say take it off the bottom. Do it off the bottom because you have to follow their spec. That's I'm just telling you right now. Follow whatever the manufacturer specs. And Jonas, off the site, you do it off the site because at the end of the day, people will come back and look at this equipment. And if it wasn't to the spec, then it's on you as a contractor or a technician. So just make sure that you follow the specs for your thing. So why wasn't this done for HFC, Jonas?
So the difference between HFC liquid and CO₂ liquid is basically HFC is not a transcritical system. So you get the subcooled HFC liquid coming back from the condenser, and it's warmer than the environment, right? If you condense at 30, 40 degrees C, your liquid will always subcool with the ambient condition because the ambient with HFC liquid is always colder. So it cools down, it produces more subcooling, and it will not create a lot of flash gas. CO₂ is different because we have this 2-stage expansion, and once the pressure dropped into the liquid receiver, you have lower temperatures of the liquid. So we do have 2-3 degrees C of liquid temperature. There are internal heat exchangers for subcooling, but still the environment is warmer. So the heat travels into the liquid line and basically boils off a certain small amount of liquid CO₂. And any pressure loss would cause some flashing of the liquid. So that's the main difference between CO₂ systems and conventional condensing systems with HFC. And that's why you have to expect to have some amount of flash gas in the liquid lines. By looking on the oil is generally evenly distributed here, but sometimes you see some, let's say, a higher saturation of oil sometimes at the bottom. So that's also why, in my opinion, it's much better to connect the liquid branch offs from the side, because otherwise you would get a lot of oil and liquid to the first evaporator, and the last evaporator is getting pretty dry and just flash gas. So that's generally a good way to distribute the right amount of liquid and oil and flash gas to the evaporators and the EVs.
So because I had someone call me up last night to ask me this question: why is some manufacturer doing installs? Why does some come off the side? Why does some come off the bottom? The two biggest things for you is the flash gas for maybe the last 2 systems. So basically, if you're doing it off the bottom, you believe that as it goes down, the last couple may get a bit more of that flash gas, correct?
Yes.
And then also is when you come off the bottom, the saturated oil is heavier or is with the oil, and it's traveling down into the evaporators a bit more, where this is kind of like a small I guess it's not a trap, but it's a place where it won't feed into the evaporators. Because a lot of times our liquids are overhead. Like we're in a big store, we're running them overhead and then we're dropping them down.
Yeah. But like the oil effect is not very big. The bigger effect here is definitely the flash gas.
The flash gas, yeah.
But you will get, if you branch it off to the bottom, the first evaporators will just have a little higher amount of oil inside. So the risk of just trapping more oil inside the evaporator, losing maybe some efficiency on those evaporators is a bit higher due to oil, not due to liquid, because the liquid will be very, very pure at these evaporators. But you essentially just increase the amount of flash gas to the very end, and then the last evaporators in line don't get the capacity anymore.
Okay, and I do have another question. So, does it make a difference for a system that has like one out, two back? So, like kind of, I call them a loop system. So, I got one liquid going out, and it feeds everything in that. So, you got one or two loops, and that's the whole store. Versus where you have 40 circuits per store. Does it make a difference, or does that you still would go this way?
Um, it is a big difference because if you have basically like one loop system where you supply the liquid and the suction lines all over the supermarket installations or the warehouse installations, these effects are bigger. So you need to consider the branch offs way more precise. If you have like a valve manifold station to supply 40 different loops into the entire building, then this branch offs, they are very concentrated on like a very small distance. It would still happen. That's also why we still go off the side here in the liquid lines, even if we deliver these liquid manifold stations or the liquid suction manifold stations for individual loops. But the effect will be lower, basically.
Definitely. It's lower on the sorry, just on the individual circuits versus the loops. Okay, perfect. And I know this is a bit off topic. Does it make a difference between now an overfeed system or a CO2 pump system versus a transcritical system? Like so.
Yeah, 100%. On the pump system or liquid overfed system, you typically have to consider way less the oil return. And even if you produce oil slugs, it doesn't really matter because the system is designed to handle an overfed liquid mass flow, right? So you have big liquid accumulator vessels sitting on top of the pump. So you just circulate all the liquid and the oil, and that's not a big deal with the oil return. The only thing on these flooded overfed systems is you need to figure out how to return the oil from that flooded circuit, right? Because you circulate the liquid all the time, and you also circulate and saturate more and more with refilling liquid CO2 into that loop. You're also refilling all the time more and more oil. So you would never get that back because you just pull the vapor out of those accumulator vessels. So you would need there are different ways. They are like oil domes. There are these internal heat exchangers to boil oil bleeding off, whatever you do. But that's the more challenging part. The field installation is less challenging.
Yeah, totally agree. Got a great question here because at the beginning we talked about PAG 68 and POE 85. Does that make a difference in this, or are you? I would assume you're still going. It doesn't matter the oil, the way you're going to pipe it. You're going to want it off the side.
It doesn't make a big difference in the vapor lines, but it makes a big difference in the liquid lines because it's totally separating the PAG oil versus the POE oil. So way more important to not build little oil traps inside the liquid line. As soon as you have the vapor traveling through the vapor lines and you maintain the required velocities, you would still carry those oils back. You just have, as I've mentioned as well, a lower amount of CO2 solved inside the PAG oil. So especially for low temp applications, the oil is just thicker because there's such a low amount of CO2 inside. And CO2 at that point solves the oil to a more thin liquid, and that is beneficial for the oil return.
Perfect. And so for like this picture here, this is POE 85. I'm assuming the same would work for PAG 68 because you're saying the velocity will pull that oil back off the side anyway, right?
Yes. So this effect here that the oil is more concentrated to the bottom is heavily with PAG oil. with normal POE oil, it's more evenly distributed. You just might see a higher saturation at the bottom.
Beautiful. Love it. So I thank you for answering that, because there are so many people that asked me that question, and I never really had a full answer to it. So thank you.
Sure. So I just talked about the evaporators. Everyone knows this air evaporator design. And as soon as the CO₂, the liquid CO₂ is traveling through these pipes inside, it always traps in like connections to these U-bends or other conditions. It always traps a little amount of oil all along the way here. And especially if you have this header connections, you can accumulate some amount of oil, and it always tries to, or it always tends to basically build these slugs. And then once in a while, an oil slug travels back out of these evaporators. That's where all the oil slugs basically start on the suction lines. So this one shows a not free draining evaporator, but typically evaporators used are free draining. That means that the suction outlet is always at the bottom of the header manifolds of those evaporators. But nevertheless, there is some sort of, let's say, pulsation of oil return, or basically just load changes. As soon as the load increases of those evaporators, it will start to inject more through the expansion valve, and then some oil, which is trapped inside the evaporators, comes back right away and forms or initiates the oil slugs in the system. And
so I've seen this before, even in the field in HFC. I've seen systems that were piped incorrectly or at very low temperature, where it just logs in the coils. Low temp is usually
worse, yeah.
the worst, right? What are some of your recommendations if that does have? What are some of the things the technician you say should check? Because you will notice all of a sudden you'd have multiple cases. We'll say in this one case we'll just not pull down. Like if that one's full of oil versus the other one. What are some of the things technicians could check just to try to verify if it's oil or not oil, or how do I get that oil back from that case, for an example?
That's very difficult, because if you run in these issues, it's typically a field piping or design mistake, right? So it's very hard to fix that. You could check the trends on like a system manager or another super monitoring system about the opening degree of the expansion valve to figure out, is the expansion valve trying to inject liquid, or is it any other reason? If you see that the expansion valve is all the time open, then you can do a lot. If you see that the expansion valve is not open on, let's say, all the other expansion valves operating at 60, 70%, but this one just on 15, that would be a good indicator to dig deeper into that. Why is the expansion valve not opening? Maybe a broken temperature or pressure sensor. Maybe your setting is wrong. But as long as the expansion valve is injecting all the time in a normal way, you should have the oil return happening in an appropriate way. So that's
super important too, because follow piping practices, look for slopes. Even though it's a new install, you know what I mean, it's been running for a few months, you got to look up and you got to kind of look at the piping system and how it's go. I've actually seen, not on a CO₂ system, but I've actually seen people pull like soft copper and push it through the truss and just lay it right on the truss. Like there's a trap every 3 feet, like, or 5 feet. Like you can't do that stuff. So just look at it, because it'll give you a good idea.
And a potential leak in the near future, because it's grinding off from these trusses, right?
Yeah. Oh man.
But pretty much the same thing I've talked about before with the liquid line branch off. Same thing. If you have 5 evaporators sitting in one common suction line and you connect them from the bottom, every single suction line will add some oil into the suction line. And if you have the, let's say, closest evaporator to the compressor and it's connected from the bottom, you would again just drain all that oil into that evaporator, and then you would see those effects as well, right? But that's something that needs to be considered doing the field piping. And I've pulled up a little animation here to explain a little the oil transportation inside the pipe itself. So oil is traveling at the outside of the inside of the pipe. So basically, it's as a thin layer traveling inside of the wall pipe, and as soon as it gets vertical, it gets difficult to really carry that up. So there's a so-called Jacob's velocity that's a bit theoretical, but that's basically the minimum possible velocity to still carry up this oil layer inside the pipe. And if you reach the Jacob's velocity, like in this little GIF, that's like a little rope traveling up the pipe. And in general, this oil layer gets from the bottom to the top thinner and thinner. And at some point, it's just not existing anymore. So it breaks and it's not traveling any further. So at that point, you basically don't have any oil return at that vertical line anymore. We have
And that's important because if you don't size that riser correctly, you have a 20-foot riser, you may have a trap in the middle and an inverted trap at the top. But if you don't size that right, if you don't have the proper velocity, like people all around, designers all around the world have their different approaches, but on average, you need 1,500, I think it's feet per second, or 19 meter. What is it? Yeah, I don't quote me on this. I forget right now, but you need to have that proper velocity, because what you're saying is on the right hand side, that oil gets so far up and then it just slides back down the sides of the pipe, because the oils always travel on the outside of the pipes, not in the center, right? It's on the outside of the pipes.
Yeah. And maybe looking onto that formula, this formula is basically expressing the minimum possible velocity to return the oil. And there's basically just one number underneath here. So that's the density of the CO₂, of the refrigerant, and our refrigerant is CO₂. And we have learned that CO₂ density, vapor density, is very huge because of the relatively higher pressure. And that's the only number in that formula which is below that part. And this high density basically reduces the minimum needed velocity quite a bit. So if we have whatever, like 6 or 8 meters per second in mind for the minimum velocity for HFCs, CO₂ sometimes still works with like 2 meters per second because the vapor is so thick, it just carries more oil with lower velocities. But on the other hand, the part load conditions for CO₂ are sometimes worse. So it's more like leveraging ours.
There's a happy medium there, right? Because then that'll come into where you'll have double risers and stuff like that. And I think we'll talk about that in a minute or two.
Yeah. Like this is basically the same thing. We built a riser in our lab to figure out like, okay, that's the theoretical math behind with the Jacob's velocity. How does it look in real life? So we basically machined some sections for a riser pipe out of glass and had a VFD driven compressor next to it to just get exactly to that point. And like this is how normal oil return looks like. You can see at the inside of the pipe, there's like this little tiny rope climbing up the line and carrying back the oil. And as soon as you drop below that so-called Jacob velocity, you see that the oil return is right about here to stop. So it's traveling up to here, and then that's it. The layer is ripping apart basically. And if you run into very low part load conditions, that's when you're coming to these double risers, right? So the general idea of these U-traps, even with just a single riser, is that every few meters, like every 4 meters of height, you would have this U-trap. And as I mentioned before, the oil is traveling in a thin layer up the vertical pipe, and it's getting thinner and thinner the higher it climbs. And by this little U-traps in between, you basically just rebuild this oil layer, and then it can start again to travel up. So theoretically, you can go as high as you want as long as you build every 12 feet or 4 meters a U-trap. And if you can't maintain the minimum needed velocity, even in a pipe with U-traps, then you would split those pipes up, right? So if you have whatever line size in the main line, you typically step down one line size for the main rising line, and the second bypass riser will be typically two sizes smaller. And the idea behind that is as soon as you drop below that minimum vertical velocity, you trap more and more oil inside that U. And at some point, you basically bypass the whole flow through that bypass rising line. And this bypass rising line has the smallest diameter. So you have still enough velocity to carry that oil back up to the compressor rack. And it's also important to have at the very end, either when you connect to a gas cooler on top of the building or in suction lines, same thing, to have like a little U-bend at the top to prevent when the system stops or when it ramps down that the oil is not flowing back the whole way, right? That would be very bad.
Yeah, and that's so important to have a inverted trap at the top, and then just even as you see where he has the bushing there, the bushing's on the horizontal, not on the vertical. Because honestly, when I first started installing sorts, I wasn't sure if I needed to put the bushing on the bottom and just have the riser or put it there. So I've done it both ways. Then I learned that you need to put the bushing on the horizontal because that can have oil in that line. Just that little 1 mil, whatever it is, there could be oil that needs to go back and not going down into your trap. So good.
Yeah.
Love that.
And yeah, that's another picture out of the field when finally one of these oil slugs you want to prevent by proper design basically comes back to the system. So we have built in a field a little oil accumulator in the suction line and monitored the oil level just to see how the oil behaves in the returning suction line. And here you can see it's pretty steadily rising and rising. But then out of nothing, we have seen an additional 5 liters within 30 minutes. And that's basically of load changes or such a big oil slug gets whipped out of an oil trap in the field piping. So this 5 liters within 30 minutes, that's definitely too much for a compressor, right? So having a look on the cut model of the compressor again, the suction with the oil travels in the suction side here on the motor side. And you would think, okay, like the idea is that the oil settles down and flows back into the crankcase and does its job for lubrication. But there are two things. Like if you get too much oil back, it can bypass into the crankcase through these little tiny check valves quick enough. So it's remaining in the motor part. And you do have a super fast spinning rotor here. Like it's the oil will not just calmly sink down, it's rotating in there. And you have the main CO₂ flow basically just pulling that oil right into the piston and just pushing it back out of the discharge line. So if you get oil slugs into the compressor, that goes immediately out of the compressor again. And that's typically looking in the field like that. So you can see here the piston. Pistons don't really like to compress either liquid or oil. And if you get such a big oil slug back, it just stresses the piston rings, the valve plates will get stressed and break eventually. And the worst case is that you just destroy the whole thing, like the piston rod, the crankshaft, sometimes even the bodies. So there's a lot of force inside these CO₂ compressors, and it's not dangerous as long as you don't get super huge oil slugs back.
Yeah, and one of the things is that this could happen for failed level control. All of a sudden, the solenoid turns on, and it for some reason stays energized. You have a failed the relay inside it fails, and it just stays open and just continues to feed oil and oil and oil into it, and then you just get too high of an oil level. One of the things is you just want to pay attention to this stuff. If you have a failed compressor, was it an oil slug or was it a liquid slug? By looking inside, it's going to tell you how much oil was even in there. And I like what you said earlier. Look at the oil. What color is the oil? Is it black? Does it smell funny? Right? How much in that compressor? Right? All those things will tell you a story on what happened to that compressor.
And you can clearly see what really destroyed the compressor. If you get liquid back, at the first glance, it looks the same, right? You have like mechanical severe damage inside. But if you get small amounts of liquid back all over the time, you can see from the direction where the oil is traveling through the lubrication channels inside the compressors, you can see how the bearings differently wear off from that liquid because of the lack of lubrication. If you basically get too much oil back, you can see that in here that the piston area, the compression area is sometimes full of oil. You can see that on the valve plates. And as soon as you send a broken compressor back to the manufacturer, they will tell you what happened. They do their reports, their analysis, and you can tell pretty precise most of the time why a compressor failed. And then you need to go back and see what the cause in the system was.
Yeah, for sure. And if you pull off a head, just like Jonas said, if you pull off a head and that is full of oil, that your head's not supposed to be full of oil. It doesn't compress that stuff. So you got to figure out, how did it get there? What caused it? Is it the rings? Is it the discharge damage? Is there something else going on? Because they don't compress liquids. So it should not be full of oil.
I mean, it will not be dry, that must be said. We do have the oil carryover, so you will see oil in the discharge and the cylinder heads or the discharge manifolds. It also depends on the operation conditions, and there are different compressor manufacturers with different oil carryovers. Some compressors are just good with running way drier than others. Others, they say like, hey, we want to lubricate that thing because that keeps it alive. Like, there are different compressor designs, even if it is a reciprocating CO₂ compressor in the field. But that's very
definitely. There has to be oil because that's what keeps it sealed, right? So, but if that chamber is full of oil, there's just too much. But you always have to have lubrication.
Yeah, exactly.
Awesome. Love it.
So I put a little summary together. Basically, what we've talked about today, compressors mostly fail to lubrication issues, which are either liquid caused or general oil caused because of the storage conditions or the refilling conditions. So higher pressure always saturates more CO₂ in the oil, which is a lower viscosity, which we want to avoid. And same for higher temperatures, it creates a lower viscosity. So oil should be stored as low pressure as possible to get the CO₂ vapor off. And especially combined separator reservoir vessels is something I would try to not use as long as possible.
Awesome. Jonas, this was amazing. I learned a ton. We have quite a few questions that we answered a few of them, but I think it'll be good for a review. The impact of too much oil in the secondary circuit. Well, like Jonas says, if there's too much oil out in the system, it's not at the compressors. So that's the impact. You're going to trip off on your oil level control. You're going to trip off on your oil reservoir or your compressor itself because it's out in the system.
It depends. If that's let's say, a stable situation, then you would have refilled already enough oil to keep your level in the oil reservoir. Don't run into an oil alarm on the compressor. If that's due to a blown oil cartridge, you would very immediately see that the oil level alarm of the oil reservoir triggers, and then right after that you will see the first oil alarms going off of the compressor, and basically the whole system will come to a stop at some point, right? The effect in the field installation is basically that you see some efficiency losses on the evaporators, because if you totally oversaturate the liquid CO₂ with oil, you will lose a lot of heat transfer inside the heat exchangers, and that's also called oil fouling. Um, and that leads then to heavy oil slugs to the compressors, and then we're ending up with maybe some damaged compressors. So
Yeah. Another question we answered as well is like, how do you recover oil from coils if they're not returning or plate heat exchangers?
it's basically just design, like make sure that the oil routing, the pipe routing is properly made, have a little slope in the long horizontal lines, keep or have the right amount of velocity in the vertical lines, use risers, split risers if needed. There are some, let's say, control ideas if you run very long times in part load conditions and you're able to basically control the evaporator very dedicated. There are some sort of oil flush cycles where you open or force the expansion valve open, but that's just possible if you have the proper system configuration with like a suction accumulator to protect the compressors, right?
Yeah. I've seen a lot of that on like HVAC with variable speed. If they're running so low for so long, it'll have a oil recovery cycle. If there's a long downtime, what are the necessary steps to take before starting up again? Well, one of the things that it all depends on what the downtime is. If you're changing an oil separator, one of a filter, like one of the things is that you need to prepare. Anytime you're working on these systems, you got to have, just like Jonas said earlier, you got to have the gaskets, right? You can't just go and take something apart without the gaskets. You might not get that back in if that's full of CO2, right? So you got to plan. You got to have the strainers, the filters. You got to have all the different components that you're going to do before you do the shutdown. You know, because if you're shutting it down, and you take something apart, say a strainer, and you can't get that strainer back in, and you can't get one, then it's better just to run the system, even if it's limping along, than not having a system running. Do you want to add anything to that?
No, that's pretty much it. Yeah.
Oil testing. So this is really, really important. So this is a great question, right? Like oil testing, I don't think is done enough. Definitely not done enough in HFC. Hands down, when I was in, there's not enough when I was on the two. I was like, a lot of people just do it like a simple oil test, which an acid test. I apologize. Simple acid test. Okay, simple acid test will tell you if you're moisture, but it doesn't tell you if you have metals. It doesn't tell you if you have all this other things, phosphorus inside the sea. Is that oil actually breaking down? That needs to go to a lab. What are your thoughts on that?
So, I mean, if you have like typically these little tiny toxic indicator strips or this little tiny tests which turn whatever color, um, that's a good start. Like if you check the general color of the oil, the clearer it is, the better. If it gets dark, it's definitely time to change. So just a visual inspection is very important. And these, let's say, quick tests, service techs has some having on hand, they're helpful to understand if the oil is like needs to get changed immediately. The good thing is, what I also don't see regularly, um, doing a proper oil analysis in a lab or from a lab, that will turn that around more into the predictive maintenance because you can see if some values from the lab changing, like general moisture saturation or some other chemicals. And they also always check the viscosity at the right state. So you can even see if the viscosity is within the range or not. And this will tell you much more upfront when you really need to change the oil. And I typically just see that when an oil is already broken, when a compressor is already broken in the field, and then they do the oil test, and then they see, okay, the oil is not okay.
Yeah,
So
no, that's something I push in my training programs all the time. Is you need to do that check because you don't know if the compressors are starting to wear or fail. You know what I mean? What's going on with that? Also, a big thing is that you got to degas that because it could be full of CO2, and you got to either heat it up or put some kind of like dust cleaner in it and just blow it off to get the CO2 out of the oil, or it'll give you like a high acid number. I've seen a few of those. So
yeah. That's another thing. Yeah.
So, because I had a guy in one of my programs, Brad Adams, pretty cool dude, and he was like, Trevor, I tried the acid test like you said, and I just changed the oil. He's like, I just put all brand new oil in the system, but it's failing on acid. And this was a few years ago, and I was like, that's strange. So they got a hold of Sporlin, and then Sporlin let them know that you got to degas that oil because the CO2 is giving it a high acid rate. And so learn something there. Do you guys do anything with? I got a question on scroll compressors. Any unique? Do you guys use anything scroll compressors at all yet?
Not really.
Okay.
We do use some, not here in North America. We do use some rotary compressors and stuff for very small applications like train kitchens or single units for one or two cabinets. That's what we have done in the past. But mainly, our systems use reciprocating compressors, semi-hermetic.
You see that in the large systems, right? You're targeting supermarket and large industrial commercial applications, right? Like
Yes.
because they don't have the capacity. That's the one thing about them is the capacity side. So if you need a million BTUs or even 500,000 BTUs, you're going to need a lot more compressors versus a semi-hermetic at this point.
Yeah.
Awesome. Jonas, this has been awesome. I learned so much from you. I really appreciate it. I really appreciate everybody hanging out like and learning from us and growing. I learned a ton today. Hopefully you learned a few things. This is what it's all about, CO2 Unfiltered, really getting the top people from around the world just to share their knowledge, have a conversation about it, what they've seen, because there's a lot of experience here at the in Refrigeration Mentor and the people that come to our community. So head to refrigerationmentor.com/hub, join the community. We've got CO2 experts in there to share the knowledge to help you. Jonas, I want to thank you once again for taking the time to chat with us.
Yeah. Thanks for the invite.
Really appreciate it. As always, let's get a conversation going, everyone. See you later.